Okay, good morning everyone. I welcome you on the last day, last lecture and last tutorial that we passed today through. And this lecture, number 7, will be related to, we now move from modeling and measurement to practical mitigation algorithm that I will present. Up to now, we could see that wind turbines create complex Doppler clutter and how we can simulate this clutter and measure this clutter. So in this lecture we will have only one goal. Given such data, how we can suppress the wind turbine component without damaging real targets or without, ignoring the resolution cell, but we won't suppress only our mitigation technique will be based only on mitigation of this DSC component. So we will focus only on mitigation technique based on software solution that will work, inside the radar. Idea of this mitigation is based on prediction of dominant spectral component that produce especially blade and blade tip at the end of blade, and we also will design adaptive digital filter that is produced by these blades, and we will by this filter remove this DSC component. So I will introduce you during this session AMPD peak detection algorithm that we use for detection of DSC component in spectrum, and also filtration, so prediction of DSC component in next time instance will be based on UKF filter, so it is unscented Kalman filtration method. During the end of the lecture I will present you some results based on real data measurement, so how our mitigation algorithm suppressed. Okay, so first I will remind you what is DSC and what is flash. Second, I will introduce you principle of the AMPD algorithm. It is peak detection algorithm and how we can use this algorithm based on extraction of DSC component from Doppler spectra. Then I will explain briefly how to use Kalman filtration, principle of Kalman filter, and special unscented Kalman filter that could be used for prediction of evolution of DSC component. Last thing will be designing parametric digital filter for based on this predicted DSC frequencies that will remove this DSC component, and of course we will check all results how it looks after mitigation. So we make small recapitulation. So during class day I introduce you phenomena that is produced by wind turbine. It is flash and DSC component. Flash is very strong short reflection with large Doppler frequency that fulfill the whole spectra, and generally any suppression of this flash will lead also to suppression of the real target. So we will focus mainly only on suppression of DSC component, but not exactly the same DSC frequencies, but of course something around this DSC component, because I think that is clear that this frequency most involving your spectra. And we want the rest of spectra will be same, because there could be detected on the rest of the spectra except this various location of DSC component our detection of our target. So if I will go to next slide, there is small recapitulation of wind turbine mitigation approaches. So I first introduce infill or so-called gap radar. It is just next radar that you will place to environment where is wind turbine on, especially wind turbine farms. So it is additional radar in your radar network. Next is antenna diagram shaping. It is sector blanking or adaptive nulling, so that beam avoids strong wind turbine reflection. But this lead that you can't see in this exact direction in this resolution cell. Then next method was adaptive limitation of side lobes. When side lobe blanking, side lobe suppression and whitening to reduce clutter sensitivity. It is good for CFAR algorithms because they're for adaptive CFAR algorithms. Next one, very promising, was for 3D radars and HPRF and wavefront strategies. These methods are very effective but often very expensive, and long time development of this method for this specific placement site where is located your radar. So it also requires complex like verification and so on and so on. But they are promising. It is like this one and last one we will focus on signal processing approaches. That is relatively publicly unknown because when I already present you state of the art from the industrial companies, there is always only notes, okay, we can make suppression of wind turbine reflections, but principle is unknown. It is clear know-how of these companies, so nobody tell you how they do it. If it's only based on hardware, software, combination of methods, which kind of method and so on. But probably it will be based on some this antenna diagram shaping, adaptive limitation, and then if it's 3D radar, by this method. Or of course it could be based only on filtration, on some just pure software defined methods. So what was our methodology of work for designing for mitigation algorithm? First, you always need to start with understanding of phenomena based on data analysis. So we just made this step. Phenomena are clear. I already many times mentioned flash and DSC component, so we are focused on DSC component. Then designing of mitigation algorithm based on adaptive filter design, specification of mitigation conditions, so what is level of suppression, what is suppression of the detection, what is local suppression of the input signal, and so on and so on. Then is designing of support algorithms for estimation of wind turbine signal parameters like Doppler frequencies, amplitude, and so on for adaptivity. Because if you want to suppress in something in some time instance, you need to have already prediction of this value that you want to suppress. Of course, you are not do it like you do it in real time. So you always need to have a prediction of values that you want to already suppress. So it is like this one. Then we make model implementation. Of course, it will be followed in case of successful verification and validation of model. It could be implemented to real radar system. In our case, it is more like academic work because we don't have designed own radar technique. Verification. The principle of verification is, does it work properly? It is suppress desired components, checking implementation, Of course, first version is developed in MATLAB, but then you will probably convert it to some DSP processor or to some FPGA and so on to some specific hardware. Then is validation. It is question, does it work right way? It is suppress wind turbines without additional artifact, and so on and so on. So this is just reminder what is flash. Flash is phenomena which just make reflectivity through all elements of blades. So you can see that there is always and occurs only time by time. It depends on rotation of PRS antenna, visibility of wind turbine PRS, and also on own wind turbines. So we use only 3 blades wind turbines consider, because it is majority of these wind turbines. We need to consider speed of wind turbines, and there is some typical values of PRS parameter. So rotation of PRS antenna from 3 up to 30 RPM, it is like typically values. In some cases could go to higher rotation speed. Visibility of flash of wind turbine by PRS during the flash could be about like 20 milliseconds per 1 RPS, and I need to tell you that of course rotation speed of wind turbines and antenna is not synchronized, it is always unsynchronized. Okay, it could occur that in some special occasions will be synchronized, but it is not typically, so you don't need to count. If will be synchronized, we already saw it, this output, it will looks like static target, because when PRS antenna illuminate wind turbines, it will be blades always in the same position, so it will looks like static object. Probability of flash visibility by PRS, if you will compute from some typical values, it is about 6%. During this 6%, you can just ignoring this affected range cell, because how you can see it is full of spectra, so it is very high level of reflection, and even if we will remove it, these parts, then it's clear that we also remove information about this target. So next one is dominant spectral component. Dominant spectral component is caused by the blade tips with the highest tangential speed. I think that this is clear, we already presented. So this behavior, because rotation of speed is periodic or quasi-periodic during changes of wind turbine rotation, of course, quasi-periodic process, then we saw it already that we have like 3 sines wave that correspond to this end of the blade is, and it is our DSC component, and we exactly want suppress this one, but not only this one, but something around frequencies around this DSC component, because they have biggest influence. This one is a reflection from our tower, and how you can see later, we first need suppress by MTI filter this tower, because our mitigation algorithm will be based on prediction of this DSC component, so exactly these 3 points, but it is the highest Doppler frequency that is in our reflected signal, but in case that we don't remove 0 Doppler frequency, for algorithm this will be like next frequency or zero Doppler, if you get my point. So it not will be 3 points but 4 points. So, and it will be really strong. So he will focus this mitigation algorithm always to this point, almost always. So we need to remove, and then he will focus only on this 3 exact point that we needed. So there is an example of our DSC mitigation system procedure. How you can see on the input we have radar data, IQ data. First we compute the Doppler spectrum and usually after passing the data through an MTI filter to remove static clutter. So on this block you have already spectrum, but with removing of MTI static reflection. So next comes the blue box, and I will call it DSC extraction. So we will apply the AMPD algorithm in this case to locate the 3 dominant peaks in the spectrum. So if you can imagine these 3 peaks in the spectrum, we just want to find these 3 maximas. If we will found it, then we can suppress. We can even evaluate in the next steps where we'll make prediction of this DSC component, where will be in next time instance, design filter, and when this next time instance will come, we just use filtration and so on and so on and so on. It is like repetition process. So when we have located this DSC or extracted this DSC components, we at the current time step we fed them into prediction block, and it is like extrapolation of DSC parameter, and it is based on unscented Kalman filtration method or unscented Kalman filter, which estimates based on present value what the DSC parameter how will looks in the next time step. All this predicted DSC when we design a Doppler digital filter with some specific function that will be focused on frequencies, on suppression of this predicted DSC component. So basically I will extract DSC components, predict where will be this DSC component in next time step, design filter on the present predicted values, and in next time instance I will use this values for filtration, then conversion, and output will be my spectrum with subset of DSC components, so it will be this mitigated wind turbine influence. And this is repeated to forever how you have this, how this reflection of course occur. So after filtration we have conversion, this mitigated signal, conversion of mitigated radar signal from spectral domain to time domain, and it is done. And you can repeat these steps again and again and again, of course. So there is some typical mitigation example parameters of result that I will show you in the next slide. So we consider in like 7 RPM of wind turbine, rotation frequency about 10 RPM, carrier frequency again we are in S-band 3 GHz, rotor diameter 90 meter, gondola angle and initialization angle was chosen like this one for example. So there is result of our mitigation algorithm. If you can see on the left side, it is original input signal before mitigation. So you can see tower reflection, one blade, second blade, third blade, and so on. And after mitigation, after we pass through all mitigation algorithm, we get this one. I will also present you results on real data, but this is just for visualization. So you can see that all the highest frequency is like blue one. It is mean really suppressed with comparison with this one. There was about 0, there is about 40, 50, it is depends 40, 50 dB. Of course, you can make complain, what about these frequencies? Yes, there is still these frequencies. It is from blade element that are moving some lower speed, but we can't suppress all. If I will suppress all, I can't recognize what is target and what I want to suppress, what is reflection. But we consider that target will have a higher amplitude of higher. And if not, it will be in this range cell, of course, lost the information target. But it is still better than just work with this. It is definitely better work with this because it is not 100% mitigated, but still mitigated, the biggest influence of this wind turbine. So this is output of our mitigation algorithm. I already presented you this final results, but now we go step by step how it works. It is just example that mitigation algorithm works. So first thing will be DSC extraction. So prerequisition on input data will be sampled IQ data of radar signal. It is our output. And first I will use MTI filtration, so I remove static clutter. If I will by MTI filter remove static clutter, you will see that there is no static reflection if you compare with this picture. And now I can put this suppressed static clutter signal or signal with suppressed static clutter. I can pass through for detection of my DSC components, because you can check what will be result in each cut. Always this value, this value, this value. In this cut will be this value, this value, this value. It is like slice, and always you get this red one because it is the highest, of course, level of amplitude. It is this 3 maxima that we already saw it during tutorial 3. You can see that sometimes for sure our algorithm also fail. When do you think that algorithm fail or not will be so, not work so well? During flashes. Why? How you can extract 3 points when it's everything like on the almost constant level? He will guess, of course, but flash is very short. So our Kalman filter, even during these flashes, will predict where will be the DSC component and will hold it with this for this during a short period of time. And then when flash just disappear, he will again start working. So during this flash, of course, you can expect more like problems, but with these flashes we can't do it anything. Also, I just want to show you that in this case like this, we have 1, 2nd, 3rd. It is clear and so on. But there is like time instance like there, no, okay, sorry. There you have 1 and there you have 2, 3, because there is almost intersections. So imagine one frequency will be very different and 2 other frequencies of DSC component will be really similar. It sometimes could happen. It is due to this interconnection of these DSC components because it is science wave. And why I'm talking about, if you will have these very similar values, then it's clear that next one will be opposite with opposite sign and very high. Why? Because all DSC component, it is like free voltage power generator, how I already present, and this free waves has difference 120 degree. So sum of all DSC component must be 0. So if I have two some very close, next one must be opposite sign and very high to just pass through the condition that result must be 0. Why I talking about it? Because when you will see AMPD algorithm that extract these 3 points, sometimes will show, how to say, little strange values, just like completely outside of range of DSC components, intersections. It is clear because still he need fulfill this to this condition. So before we start suppression, we of course need to make identification of these 3 components, and this identification is based on automatic multiscale based peak detection, and for this reason I call it AMPD. And this AMPD authors is, I will show on the next slide, we are not authors of this algorithm. This algorithm was presented, publicly available, presented in 2012, and the goal of this algorithm is detection of highest peaks in spectrum or position estimation and so on. Generally, this algorithm works for any type of signal. It is just algorithm, and it is used for extraction of highest peaks in any function. So it not could be only spectrum, of course, but any kind of signal, how you will see. So in principle working like that, find points that behave like local maxima consistently across many window sizes. So imagine that you have window and try found maxima in this window. So you will try, and what will be results? Okay, some maxima, but what on which parameter depends of how many maxima I will found it? On size of window. Because of course, if you will take small size of window, you will detect something is large, you will like make averaging, and you will detect another number of windows. So it is dependent on the size of this parameter, and we need to find, like, how to say, best value where it's fit to our cases. This algorithm works very well only for periodic or quasi-periodic signals, but it is perfectly fit to our case because this DSC component is free sine wave. Or so it is clear. If in case that your signal will be without any noise, you don't need this algorithm. Why? Because you always detect these 3 maximas without any problem. But it will be noisy, then you will have jittering of your signal. And then this jittering, it is hard to make decision. Where is maxima in this jittering? And for this reason we use this algorithm. When struggle this algorithm, when these signals not be periodic, quasi-periodic, or it will have irregular spacing or widely varying peak width. But it is not our case, so because it is free sine waves, when is changing amplitude or when is changing DSC components very quickly during only changes of rotation of wind turbines. But this is not so quick process. So for our case, this algorithm was a really good one. Original authors of this algorithm is Mr. Scholkman, Felix, Jen Boss, and Martin Wolf. How I already say, there you have link to original paper with this algorithm. The paper was an efficient algorithm for automatic peak detection in noisy, periodic, and quasi-periodic signals. So you can read the original paper. Principle of this algorithm that we use for DSC extraction is core is construct is the local maxima scalogram. I will call it LMS. It is a 2D binary matrix where each row corresponds to some a certain neighborhood size. They call it scale, and each column to a sample index. And it is binary. So where will be 1, it is indicate that the point looks like local maxima. And where is 0, it is not looks like local maxima on this scale. So, and after this we will make summation across row, and this gives us a vector whose largest values correspond to robust peak. So exactly where you have this jittering and to some maxima, it will locate this maxima even with this jittering. It will be highly dependent on noise. If your amount of noise increasing, then it's clear that this you can hardly recognize this quasi-periodic or periodic behavior and then fail. MPD provides peak position without necessity tune many different threshold or setting any threshold and so on, because it is like automatic peak detection, because he make variation, he setting this threshold like myself. It is like works like this. So how there I will provide you few more details about this algorithm. So input data to this algorithm, how you can see on the picture, is spectrum computed from IQ samples from measured signal. So it is an individual spectra. So I compute in slow time individual spectra and just feed them to this algorithm. So it is one by one. It is example like individual cuts in Doppler, and you just feed them and you want to locate these 3 maxima. So as to say, entry in this metric is set according to whether the sample at position E is greater than neighbors. So it is like comparison value. It is greater than neighbors. Then and on what depend this parameter of this thing? It is depends on size of window. So there is variable size of windows, and he always gets some result, and this result is then like sort by size, and this which bigger size, it is big fidelity, that will be this maximum peaks. The conceptual point of work is that embedding peak detection into the multiscale matrix, and it will really become robust against both noise and slow trends in baseline. And imagine, this is relatively slow trend. So and what is noise? It is another spectral lines in spectrum. So it is relatively slow. So exactly AMPD algorithm fit to this our case. So first I will compute computation of LMSC, this scalogram. It will be this matrix, and where results could be only 0 or p. It is some random variable from interval. It is depends of site. So and key is index of vector of our discrete frequencies. So then I will make summation of all scalograms, and I will make sum of our neighborhood sizes, and we sum each row or equivalently sum of the wall matrix along the scale dimensions, and this will result to some vector where each component indicates how often sample I was considered as a local maximum across the wall scales. And of course, which the biggest values that will be considered as a maximum with highest number, it is my real maximus. There is like a very visualization of this AMPD algorithm. Check. This is this jittering, and you need to find what is maxima. And imagine that one maxima is detected here, 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 here. But from point of view, if you don't use this algorithm and don't see these points, for you it will be hard. It is here, it is here, it is here, because it is very, very varying. So this is like example output, like school example. If I can say of the algorithm, you can see it is just generated in signal in some time, and I add a noise and try use it this algorithm. So I don't use it on spectra, but on some generation of time signal. It is just for presentation of principle. Okay, and then next step, after sum of scalon by rows, we need make rescaling of scalogram. The resulting vector that is there from previous step, we determine global parameter of AMPD algorithm. Especially we are looking for global minimum of transformed version of the summit vector, because this minimum corresponds to the neighborhood size where the overall local maximum structure is best captured. So it is mean that index of this global minimum gives you an optimal scale. And we use this optimal scale that was pre-computed in previous step to reduce the matrix of element and for robust peak detection. This step is very important from point of view makes AMPD algorithm adaptive to the data. We don't choosing some fixed window size for all scenarios. The algorithm infers an appropriate scale directly from the spectrum itself. So we don't tweak this parameter, we just, how to say, algorithm choose this optimization parameter itself from pre-computed from spectra. So then we, in this final step, there is peak detection step. After reducing of the metrics using optimal scale, we compute standard deviation, row-wise or column-wise, it depends. And of course, we are looking for result that has the lowest standard deviation, because lowest standard deviation means the lowest error. I am closer and closer to this maxima. So, how we already test and make verification of this algorithm? We just generate some signal. It is the upper one. We, of course, we know where is this local maxima. It is the orange circles, and the goal was testing how will this AMPD algorithm detect this maxima under condition of different amount of noise that we adding to our signal. So there you can see that if we use this detection algorithm to signal without noise, then all maxima is perfectly detected. But you don't need to use this algorithm because it will be easy for detection of this local maxima anyway. But if you will use some level of noise, this is example, I think, that we generate signal from -4 to 4 volts, and level of noise was like 0.2 volts, and like random signal. And then we just make comparison of the green points and orange points, and we could evaluate for different level of noise how this AMPD algorithm is accurate. And there you have like presentation of accuracy of this AMPD algorithm. The orange one, it is original local maxima, and green one is example of like estimated maxima, local maxima of our AMPD algorithm. So you can see, and this is evaluation of error. So you can see that pretty finely this algorithm works for detection of maxima. And after evaluation that we select good, good algorithm for detection of maxima, we use this algorithm for our spectrogram. There is example of wind turbine spectrogram before AMPD algorithm, so it is classic generated spectrogram. And imagine that in each slice now we use AMPD algorithm, and you can see that in each instance you see 3 points always. This, then this, and this. Maybe it is too small for you, but in each cut there is always 3 points. So it is mean 3 frequencies that we need to detect. Of course, it is on simulated data, on real data. Sometimes this extraction failed. It is depends how strong are reflection, how are visible these DSC components, and so on and so on. But works pretty well, how you can see. Exactly follow our free sine wave. Problematic place are where is interconnected in a real measurement, and yeah, where is interconnected. So is it clear? Can I continue? It is just this DSC extraction. So after we know which DSC components are in our frequency spectra, we can move to prediction of DSC. So after this extraction, we for us is interesting how this DSC evolve in time and how we can predict them. So it is mean if you get these 3 values, my next question will be, what will be these 3 values in the next time instance, and the next time instance, and next time instance, and so on and so on. And for this we use Kalman filtration. So you already know, and from presented picture, that Doppler spectrum of wind turbine is really highly complex and depends on many parameters, and from the side of wind turbines and from the side of PRS also. So it is very high dependency. It is depends also on mutual geometry of PRS and wind turbine and so on. So some of these parameters we can measure, or we know them, of course, if we know wind of blade, position of wind turbine, position of PRS, PRI, length of pulse and so on. So a lot of parameters we know or can be measured, but a lot of parameters is unknown, but they are slowly varying, and it is exactly our DSC component. So we can say also that this slow varying parameters of DSC component, this behavior is slow, okay, but it is for sure non-linear, highly non-linear. Just remember this is non-linear. We use Kalman filtration. Kalman filter, I will talk to you a few words about history. First time Kalman filter is sequential linear minimum mean square error estimator, and it is developed by Rudolf Kalman about in 1950, and Rudolf Kalman published this result of this filtration or estimator in about 1960. From this period of time became one of the most widely used tools for tracking and state estimation in area like radar, robotics, control system, navigation. Almost everywhere is Kalman filtration. Of course, he introduced first version. It was linear Kalman filter and works only on state model that was linear. But you know reality, so nothing is, how to say, not all things are linear. Some things are slightly non-linear, highly non-linear, and so on. So from 1960 until now, it is they still discovering new variation of Kalman filter for different type of process. In the red rectangle, you can see original paper published by Professor Kalman in 1960. You can find it, this paper on IEEE if you are interested how looks original contribution. And Mr. Kalman, some history lived from 1930 to 2016. I was curious about that he lived late in USA, and he was founder of one university where was director until his death. So this next two slides will show you I will try show you on which principle works Kalman filter. I don't know, do you have experience with Kalman filtration? Do you have some courses in Kalman filtration theory? Little? Yes? 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 No? Okay, somebody yes, somebody no. So the conceptual operation of Kalman filter is like that. We have prediction step and yeah, right. I think that Kalman filter is used almost in any area of signal processing. Honestly, I just mentioned few of them, but I think that you can find it almost anywhere. Exactly. And it is same. DSC component is feature extraction, exactly. So it is similarity. Right. So in the prediction step, we use a motion model. We call it state transition model to propagate the previous state estimate forward in the time. So this gives us predicted state and associated prediction covariance. So it is how you are sure that prediction values is accurate, like generally say. Then we have measurement step. So we obtain new measurement of some parameter from the sensor. There it will be DSC frequencies extracted by EMPD algorithm. And together with measurement covariance, and again, how I believe in measurement. Because it is affected by noise and extraction error and so on. So I have two things. First, I will do it prediction step, and I have some covariance metrics that told me how you are sure that this prediction is accurate. In next step, I will get result of measurement, and from measure again, and this measurement is also not 100% accurate, but I have some how to say measurement error. And now Kalman filter will make decision. Do I believe more in prediction or do I believe on measurement? And it is based on this covariance metrics. And if I believe more in measurement, okay, and then from this all values is computed by Kalman gain. And this Kalman gain reflected if I will believe more measurement or if I believe more in prediction. Because it could change in time by time, of course, if its measured values accurate more than prediction and so on. It is depends on many variables, and he will always decide if you more believe in one or believe in two, and compute next prediction state. He will make so-called update step when Kalman filter combines predicted state, measured, and using Kalman gain, and then this yield to new state estimation to minimize mean square error under Gaussian assumption. It is important, Gaussian, because if it will be nonlinear, then there is not necessary fulfill condition that will be Gaussian distribution. And it is exactly our case. It is highly nonlinear, so we can use this classic Kalman filtration of like linear Kalman filter, if I can call it, but we use some other type of Kalman filter. So generally we can say that Kalman filter combines two-piece information for final estimation with the small possible error. There is another example how we can look at in, it is used very much often for tracking, so it is just example from tracking algorithm. From the previous estimation, it is this blue rectangular and motion model. Of course, we know what is motion model of target, because the motion model, like example of our plane, can be random, because it is just a limitation of own plane and so on. We can predict where the object should be. So the prediction, we call it, or I call it, maybe you call it by different word, it's extrapolation. And this extrapolation of the next step, it is some extrapolation ambiguity. Then we can get measurement and again some measurement ambiguity. And from all two things, we make new estimation where is position, where is, I don't want to say true position, because of course it is not always true that you will hit exact position, but it is estimation of new position based on these two things, and then start repeating again. And what is your result in tracking algorithm? Just kinematics of your target And if you will transform this to DSC component, it is same. I will get some measurement, I will predict, I will compare, I will get correction, and again and again and again. Only we just do it for DSC, not for tracking. There is another example from point of view probability density. We have estimation of target. Okay, it is 1D example. So our target just moving around axis X for just simplification. So we know estimated position and speed in this time. I call it times minus 1. In prediction state, first we will predict, we extrapolated this value and we get something like this Gaussian distribution of our extrapolated value. Then I will receive measurement and it will be this one. And of course, if will be wilder, then there is bigger uncertainty, so it is mean that this is like worst value than this orange, so our Kalman filter will, how to say, believe more in this one, and from this green one and orange he will make this blue one. It is this correction. And now it is depends if you believe more in green or orange, but you can easily recognize from the shape of Gaussian distribution. It will be more and more narrow. Is it clear that it is more precise and you can believe more on this, like example their measurement or an extrapolated value and so on and so on. And you combine together and get corrected estimation what will be. So in our case, state vector will be based on DSC amplitude, frequency and phase. And the measurements will be DSC extracted from the Doppler spectra. So it is just same principle, only I show you on target tracking because it is easy to imagine how it works. And this correction, computation of the blue one distribution, if I can say, it is depends on Kalman gain that is computed from these values. No? Okay, I will finish maybe this theory. It is about like, okay, it is about 1-2 slides. If we can finish and then we will make tea time. I'm checking that you are watching tea. So, if model of measurement is non-linear, then we need to use Kalman filter modification because we can't use this standard Kalman filter introduced by Professor Kalman because it is just for linearized model. So there is two popular non-linear Kalman filtration extension. One is extended Kalman filter, which linearize the model around the current estimation. So it is just for, how to say, slightly non-linearized model. So it is almost linearized, so it is just like slight non-linearization. And unscented Kalman filter, which use so-called sigma points to approximation the propagation of means and covariances without explicit linearization. So it is for highly non-linear problem. When you see behavior of our DSC component, it is really clear that is highly non-linear problem. So we are using UKF for prediction of this DSC component. last slide, and then we will make break. There is some description of our input and process parameters. So state space model for DSC prediction contains parameter DSC amplitude, Doppler frequency, and phase. We define this process model that describes how this parameter evolve between time steps. So largely smooth changes reflecting slowly varying wind turbine's rotation, speed, and orientation. Our measurement model maps the state to observe DSC frequencies and amplitudes extracted by EMPD. So state, we know that is 3 sine waves shifted by 120 degrees and so on. And measurement model is extraction value from EMPD algorithm. Of course, we need to define also covariation metrics. Covariation metrics is, I would describe it like by 3 parts. This one is transmission metrics. This one, middle one, is standard deviation metrics. And this is just transposition of transmission metric. So, but how will looks in reality? For our values, transmission metrics, state vector, so it is amplitude, frequency, phase of our DSC component, DSC. And if you will compute, you will get this result. So what is output of predicted? This is a prediction of one DSC component, one. Okay, you must say, okay, and where I get other 2? Amplitude is always same, it is only phase shifted. So I can easily compute the rest of 2. Okay, so we will make tea break, 15, 30 minutes, up to you. So what do you think? 15, 20 minutes, something like this. Agree? Yes. Okay.